our pleasure to introduce Hirokazu Shirado. He's an assistant professor at Carnegie Mellon University, Human Computer Interaction Institute School of Computer Science. He did his bachelor studies in mechanical engineering, and then he changed the career to do his PhD in sociology in Mellon University at Human Nature Lab, I believe. And his research spans from computational social science to social networks and collective action problems. Today he's going to talk about collective action in hybrid systems of human and machines. The floor is yours.
Yeah, thank you. Thank you very much. Yes, I'm really here to share my work about production in hybrid system of human machines here, because of course, temporal of human machines. I talked about my work to actually this semester online 2 years ago. I finally to give a talk in person. That's great. So probably I introduced my background there, and also I already got a great introduction. But I think it's great to start a little bit refresher. So my background is engineering and sociology, as the introduction said. As a researcher in both fields, I have been studying the inter-individual dynamics of social networks and product action programs in social networks. So humans have evolved ability to form complex networks of social connection. However, interconnected group of people face challenges in product action. So I will introduce more detail about what is the program. If you are not familiar with, that's fine. So when individuals and group individuals are not aligned, individuals may see no optimal way to act. So I'm especially interested in how machine intelligence can help people to address such social dilemmas. I think most of our welfare comes from social relations. So we are happy or we are sad because of the good or bad human relationships. Both?
I don't know. I mean, people are
It's okay.
can't hear.
Yeah? Oh, sorry. Can you hear me?
I think they must hear you better now.
Oh, okay, great. So I think that most of our welfare comes from social relationships, but we are struggling from having good relationship with others. And social dilemma at least partially explain why we cannot get a good relationships. In theory, the development of technologies aims for improvement some of our welfare. So why don't we consider the challenge of policy action as a primary part of technologies? And I think machine intelligence has such a potential. So one of the famous challenges of policy action is cooperation. So large-scale cooperation is quite challenging. The group that best if individuals cooperate, but for each individual, it's very tempting to get a free ride of other cooperation. So why, for example, we need to pay tax to get a public goods? We hate to pay tax. But if everybody don't pay tax, we don't get any fresh water and good electricity and blah, blah, blah. So it's the same thing happen for many social phenomena that it can start to challenges in the every part of action. So first I'm introducing my experimental result to examine how AI agents can facilitate cooperation in human groups, which were published by iScience in 2020. The title is Network Engineering Using Autonomous Agents, Increase Cooperation in Human Groups. So this slide shows my experimental sequence to study political actions in hybrid system of human and machine. So I recruited real human participants from online labor markets. For example, the Amazon contract that you might know. And I let them interact with each other with some economic incentives and sometimes as some autonomous agent or bot in a network of people to examine the effect of machine intelligence on human groups at individual and collective level. So for the whole experiment about cooperation, I used a game theory informed public goods game, or answer them is a donation game with a dynamic network setting. So let me show the actual view of the player in my experiment. So this is the actual game view. So this The game consists of multiple rounds, and every round, players have to make a choice between cooperation and defection with their local network neighbors. So in this demo, I didn't mention clearly say cooperation or defection. Like you can see any word about cooperation defection in the statement. But actually, the blue choice A is defection. So keeping money for themselves. And orange choice B is cooperation. So that means you give some money to your neighbor. Then if your neighbor will cooperate with you, you get more money than the people pay for the cooperation. And also you can see the network diagram here. And central node indicates you, and you have now $1.1 from today. And you work with 3 network neighbors, then J2, Y9, and G7, and indicated with the last choice of them. So that means here, you and J2 and G7 chose cooperation in the last one, and the Y9 chose defection in the last one. Then you are asked to whether to cooperate with this environment. Then after choosing whether to cooperate, like this game, the poker player chose cooperation again. You can also have a chance to reform your neighborhood by making or breaking a tie with other players. So we call this setting tailoring option. Then again, subject choose whether to cooperate with updated neighbors. So they repeatedly make the decision over 30 rounds. Okay. So there are 2 steps. Whether to choose whether to cooperate with all the neighbors. Then also they choose to the neighbor by making a breaking tie with individual player. With typing option, they can choose to cooperate or not again with updating. All right. Then you can see the dollar mark here. So that means that the player actually earns the money based on the play. That's the okay. This is the typical dynamic of human cooperation in a network in my experiment. In the network figures, every dot is a person, and every line is a relationship between the people, and they are artificial networks with real people. For the first round here, we created that network structure, drop the real people into a particular point of the network, and introduce them to the network neighbors. Then after the first round, as I showed you with about game view, people change their network spontaneously by making and breaking with ties with other people, given the timeline motion. Okay, so that's why round study the network structure is totally different from round 1. Round 1 is like artificial networks, high-grade. But round 30 actually the result of the spontaneous timeline between the people. So node parameter indicated their choice between cooperation and detection. So blue node are the people choosing cooperation that is sharing some money with their neighbors, and the red node are those choosing detection, keeping their money for themselves and enjoy their neighbors' cooperation. So that means the blue node means nice and cooperative people, and red node mean free riders. Okay? So in this session, about 65% of the people start with cooperation, but eventually defection takes over social system. And this is a typical. The theoretical and empirical studies have shown without certain treatment, the cooperation decay over time.
My research question is, how can AI agent or bot facilitate human cooperation? What bot strategy can make people give up pursuing self-interest and allow cooperation to take root like this? To consider the effective intervention of the bot, actually, I first investigate the actual pattern of human cooperation in a network as a preliminary study. So as a network parameters, I focus on the number of local neighbors and number or rate of cooperator in local neighbors. So here is x-axis. So this graph, I know it's a bit difficult to interpret it. So let me explain that. In this study, human play only with dummy players. Okay, so each individuals do this public goods game with controlled neighborhood. So that means I control each individual neighborhood like this. So here there are a lot of nodes, but only 3 nodes are people. Okay? The other is all dummy players that I control. Then in this game, I change the neighborhood situation in terms of the number of local neighbors. So that means group neighborhood size. And also the rate of cooperator in the local code, so that means the neighborhood quality. Then I change, I give the very different type of the group size and group quality to each individual. Then I see how the person select the cooperation or defection under the condition of these variety of conditions. So why I did this type of the experiment, except I gave this game to the people to play with each other, because we cannot investigate whole entire space of the neighborhood if I allow them to play with each other. For example, if the cooperation emerge, people typically to form other people because they are cooperator, then probably they play the game with high level of the rate of cooperator and high number of the local neighborhood. So probably they play only with the side of the play, and they probably choose more cooperation because their neighbors cooperation. Then we don't know how the player choose cooperation or defection other area of that. That's why I control this neighborhood network regardless what they choose. And it's a bit hard things happen here. That means that I also give such a natural sense to the people to feel like, oh, changing from round 1 to round 2, it's natural. So that means I choose defection. Then what's going on? I lose my neighbors or something like that. So there's some difficulty here about implementation, but eventually we found gave a naturalistic change of the neighborhood, but control. Okay, so that means I explore the whole space of the neighborhood space. Then I see how people behave in terms of choose to cooperate or not with neighborhood. So here is the result. This graph shows the experimental result. This is just, yeah.
What's the dummy play? And how is that?
Yeah. So here is different from my experiment. I will explain that. Is that this dummy player is controlled to give the trajectory of the neighborhood space. So that here is I pre-arranged how these individuals experience their neighborhood over 30 rounds in terms of the group size and group quality. So this is I pre-arranged this like a trajectory. Then, for example, this player played round 1. It's the number of the local neighbor 2 and 100%. So that means that they have 2 cooperator. Then what they choose. Then, for example, this player chose like cooperation 1. Then, like I control the dummy player to give, for example, the number of local neighbors is 6 or the 100%. So that means all neighbors is a cooperator. So that second round, they have 6 player, they're all cooperator. Then we examine how this player chooses, for example, in this case, cooperate, something like that. So that means that here is each agent. I do not control individual agent. More likely I control the neighborhood to give the trajectory to explore the huge space of the neighborhood to see how the cooperation probability distribution looks like for each individual. Then this result is that the aggregation result of 309 human subjects. Okay, so I getting the data for 13 cooperation decisions for each individual. Then here is I aggregated. Then the color indicated. So this is not estimation. Here is average. Then this is the color indicated the cooperation or defection. The blue color means the cooperation, and the red color means the defection. And here is these 2 results actually identical, but I changed the y-axis with various reasons. That here the y-axis number of cooperators in local neighbors. Then here is y-axis rate of cooperators. So that means I divided this number by this x-axis. Here is number of the neighbors, and y-axis number of the local cooperative neighborhood cooperators. So that means we can see there are empty signs of triangle. Of course, we cannot have, for example, 3 neighbors and 4 local cooperators, right? Because we have only 3 neighbors. Then 4 local cooperators does not exist. That's why here is empty. Then because of this weird triangle, I also spread out the value by like normalized y-axis divided by x. So that means that each cells indicated same things but different locations. Then I smooth the result for clarification. So for figure B, I transform the discrete value to continuous one for visualization. So typically, people are less likely to cooperate with increasing the neighborhood size. Right? Here is a changing color from blue to red this direction. So that means people are less likely to cooperate when the group size increased. At the same time, people do not cooperate when their neighbors does not cooperate too. Okay? So that means that this is not like surprising findings. It's kind of like a theory said like, hey, people behave like that, but I just confirm from empirical data. So social roping theory suggests people are less motivated to cooperate in large group because they feel that their effort will not matter of the group. So that's why typically the large scale cooperation is hard. On the other hand, social contagion theory suggests people change their choice, for example, from cooperation to defection by following their neighbor choice. So this one says like the cooperation pattern is theoretically reasonable, but this pattern brings in a practical problem to AI reformers who attempt to facilitate cooperation within a network. So let me explain why. Again, this research question is how the additional bot can facilitate cooperation in a group of people. Then when it comes to behavior of the bot, I made bot always cooperate. Okay, so bot can choose the cooperation and defection, and I sometimes choose like a famous tit-for-tat things here. I will show the result later. But basically, if bot choose defection, that means that they just make their people's environment worse. Then I do not come up with any reason to why people choose to cooperate if the bot choose defection. So mainly, I made the bot choose cooperation, always. But if just allosteric bot does not change the tragedy of cooperation, and actually they did not in my experiment data, what could the bot can do for human cooperation? So my idea is a network intervention. That is, bot strategically intervene in network connection of people. However, it faced another difficulty. So from the egocentric perspective of people, okay, not bots, the people, the bot support in this group setting is taken as additional cooperative ties, right? So if you're human, then you have a bot, then bot cooperative. So that means from your perspective, this cooperation is one of them. However, given the human cooperation strategy, both additional cooperative ties are less likely to improve human cooperation. So here, this arrow indicated the tie attachment or detachment of the cooperator. Okay, so for example, here is the group size is 10, and the cooperator is just 50%. Then, the cooperator is 5. So that means that here is 10 neighbors, and 5 people chose cooperation in the last, then whether to cooperate. Here is color indicated less than 50%. So on average, people are less likely to cooperate with this neighborhood. Then, okay, so let's to intervene their personal network, then bot attached to you to try to improve your cooperation probability, but it's not. Because if you attach someone, then the someone increase the group size and increase the group quality. So that means that this direction, right? Increase 1 both way. So that means this arrow indicated the attachment or detachment of the cooperator. For example, here is both cooperators. And you can see the color doesn't change so much along with the arrow direction anywhere. So you can see this diagonal direction does not change the color. So because actually the effect of social contagion cancel out the effect of social roping. Okay, so if you, it looks like good, like a bot cooperator attach you, but that means that you increase the group size and you are less likely to cooperate. It's a larger group size. So in the iScience paper, maybe there are another way to improve that, but I cannot come up except for this idea is that I proposed and tested a network intervention by tie management bot. So in contrast to tie switching bot that I show here, the tie management bot do not change their own ties. Instead, they give a tie rewiring option to their connected partner to make or break a tie with another individual. The brokerage offered greater flexibility to the bot in terms of changing their partner's local environment. So that means that here, the bot can also select the attachment, detachment here, this direction, and you can see that there are huge color change. So that means that the bot with the time management bot can allow to change person's environment to increase or decrease a lot in terms of the probability of cooperation. Okay, so far so good? Yep. Yeah. So from this slide, I'm showing the experimental result to test the theoretical ideas. This graph shows the result of only humans and no bot. So the light gray line shows here. So you can see a lot of perturbation. That means that this light gray line shows each session's result, the actual result. Then a black line shows average among them. Then the orange dashed line indicated the initial level of the cooperation. Then you can see the cooperation decays over time without bot. Then the time management bot suggesting to cut a link with a non-cooperative actor almost all the session. Almost all the session actually shows a cooperation improvement. At the end of the game, cooperation improvement by 40% on average with the tie brokerage intervention. So if you really know about the human cooperation, this type of study, you might be surprised this strong result because it's rare actually to show the improvement. So some experiments show that to maintain the cooperation, like from initial level. But it's really hard actually empirically to improve the cooperation from the first. The reason is that actually come from the human heterogeneity. So here is, I say like 60% people chose cooperation. So that means 35% chose defection in the first round. And these people are different from the rest of the 65% of people. So that they already have an idea to get a free ride on the other cooperation from the first round. Okay, so that means that if we want to improve cooperation, for example, in the experiment, so that means they are not random people. So some people are more cooperative, some people are defective. We change the defector's mind, right, to choose cooperation. So that's why it's really hard in an experiment to improve human cooperation because so that means that we need something to give up them to seeking for self-interest that they have initial interest. Yeah. So the bot intervention strongly affects human cooperation. That I confirmed that even a single bot can promote group cooperation with the use network intervention strategy. The network snapshot shows an example of cooperation and network change over round without and with a bot for sample sessions. So in the bot integrated session, the single bot here substantially changed the social dynamics and network topology. And interestingly, the bot itself moved to the periphery of the network over round, right? You can see. So that means that through the initial intervention by the bot, humans come to develop a cooperative circumstance on their own. So that means at round 30, even if I remove the bot, probably people keep cooperating. I don't know how sustainable, but probably next 5 rounds, people still keep cooperating with the bot intervention. So human cooperation pattern change from this to this only by adding a single bot. That is, the bot can work as a catalyst of social networks and collective action. This change by bot is so strong and salient, so you might see this cooperation problem easy. It looks like humans are easily manipulated bot to enjoy cooperation. But actually, this problem is much harder than it looks. maybe you might know. So I tested over 8 strategies, actually more than this strategy, for bots to try to promote human cooperation. And only the disengaged time management strategy works. For example, I'm including a tit for tat bot. So that means bots do not change like network tie. They do some tit for tat. So that means the person chooses a cooperation, they keep cooperation. Choose defection, they not defection. That work in this group setting. And I also, for example, hey, you might be more optimistic view to humans. Then you say, hey, don't do that like giving the option to people to cut the relationships. Maybe give more option to form a tie with cooperator. That might help to improve cooperation. So that means that engaged time management doesn't work. So what's happening with the engaged time management bot actually is that defectors are more from the claim. So actually in some sessions, I gave, I think, over $80 to one person who keep defecting with engaged time management bot. Okay. It's really sad from financially too. So, in my investigation, actually only the disengaged time management strategy help bot facilitate human cooperation. And also, you might also interested in the bot visibility. So for example, one of the EAT studies showed like when people realize to identify the bot identity, so that means, hey, I'm interacting with a bot, they change their behavior, typically from cooperation to defection. So that means that people are less likely to cooperate with AI agent. It's not only a EAT study, but other studies also show like AI averse. So maybe this, actually in my main experiment I didn't inform them they are interacting with bot. So because I just want to investigate in the effect of behavior by the bot. But because of the possibility people change the behavior, I including an extra session to show the bot identity. So that they let them know they're playing with bot and some suggestions, specific tie suggestion come from the bot. Okay, so you are suggested this tailoring option by this bot. Okay, the result doesn't change in my group setting. So that is interesting construct from, for example, here at other work. Maybe people change their attitude to AI in the two-player game and the group settings. For example, here is maybe they don't care about so much about the bot identity if they play a bot, one of them, in the neighbors. So that means that here their choice is to cooperate or not with all their neighbors. Do not select to cooperate to each individual. In that case, the bot is actually one of them. At least bot works for cooperation or some benefit. They might not need to change their behavior in my setting. This is just assumption, but it's interesting construct, I think. Okay, so our iScience papers end at this point, but I actually have explored more intervention for bot in these settings. So I'd like to share the unpublished data with you. So that's, I think, a good thing to give a talk in person and online. When I talked about the reformer's dilemma, I explained why simple tie switching strategy couldn't work, given the cooperation probability distribution. Okay? But I will trick you, because this distribution is the average of hundreds of humans. Okay? What is the differences? So in fact, different people show a different behavioral strategy in my data. So this is a scatter plot matrix of estimated individual level coefficient for cooperation probability. So here is red dot is average that I showed in this smoothing result. Then each gray dot indicated each individual cooperation estimated coefficient for each individual. So that here is gray line, gray dot line 309 points, because I collected 309 individuals for the various type of the neighborhood situation. Okay, so that means I can estimate each individual the response to the default level of cooperation and how they react to the number of local neighbors and how they react rate of local cooperators. Okay, then here is a distribution of 309 people. Then of course, because my stats works well, and the red average dot indicated the center. But it's hard to say this red line, red point, indicated, represent every people in this group. Also, the other things, interesting things is that I cannot find the clusters of these 309 people. So that means that sometimes in economics, people try to categorize human behavior in types. For example, this type of people like a conditional cooperator. This people is always defectors. But in my data, at least, and these settings, Amazon contract workers, I cannot find a clear cluster here. So that means that here is a distributed, yes, but it had to say categorize people into types with my data. That's also another interesting things, I think, from the data. But let me go back to the bot intervention and clarify the meaning of individual differences from the bot intervention perspective. This graph shows the actual cooperation probability distribution of 4 subject sample from 309 people. And this person always cooperate. This person always defect, regardless of the neighborhood situation. And this person and this person, these 2 people, actually are sensitive to neighborhood situation, but totally different way. So this person chooses from defection to cooperate when their neighbors change their behavior. So that means that it's a very social contagious person. This person changed the behavior from defection to cooperation about response to the group size only. So if the group size increase, they get free ride, but the group size decrease, they cooperate.
Actual people or
Actual people. Actually, so I can show the actual point of this point. Then I smoothing to that. Of course, here is I show the very specific people, like many people actually in the between, but here is kind of like extreme people in this distribution. But the point is that if I put bot into a network, cooperative bot, different people respond differently to this additional type. For example, like top 2 people are not affected by the bot or more likely to the neighborhood. So that means that there's no effect for them, even if they're always cooperator. Why do I give the cooperative bot to the people? Change the behavior. These 2 persons affected by the change in the neighborhood, different way. So if I giving the cooperative type to this guy, it's more, this guy are less likely to cooperate because it's increased the group size. But this person doesn't care about group size, more likely to affect this quality of neighborhood. So she probably choose cooperation. Oh, by the way, I don't know the gender, but here's just example. The person might choose more cooperation with 50 times. So that means that I should target more this person and avoid this one, the other 3. Then we might increase the correct level of the cooperation, right? For that. So that's my idea, the personalization. So I won't go into the detail of the algorithm, but I basically use a very simple Bayesian inference techniques to estimate each player's behavior model by the bot observing their behavior, cooperation or defection with the player neighborhood status. So that means that in the first few rounds, bot behave randomly, but they can observe the people's behavior, then they collect their data. Then they come up with, oh, maybe this player similar to this person, because I have 309 people. Then based on the estimation, they choose the target people. I think that personalization strategy as clever as time management. So let's see how this strategy works. Here's the result. You can realize that I failed totally. The personalized targeting intervention didn't work at all. So if I got some result from that, I might get another Nature paper, but not. Sorry for me. Cooperation decays, even with the bot estimating each subject behavior model, allocate their time based on the estimation. But why? So why did the personalization strategy not work? I think that's interesting to you. I developed the personalization with this framework. So machines sense how each individual cooperate and act based on the estimation. Act here is like switching the tie with the estimation. The machine intervention aims to increase the cooperation probability by adding cooperative ties from the default probability. So that means that I assume human behavior. So various type of the human behavior, but here is each individual have some behavioral tendency or the policy or strategy. Then if the bot can estimate each individual probability, bot can work more efficiently to improve cooperation. That's the idea. A possible reason that I failed is that bot didn't sense human policy well. So that means the bot might need more data to estimate the better behavior model for individual. Maybe the simple Bayesian estimator doesn't work. Maybe I need more sophisticated machine learning model to estimate that. That might be true. Or bot should do different actions based on the sensing. For example, bot might take more sophisticated tie allocation than the simple tie switching. So here it's not only the sensing, but also we need to think about how bot behave to improve human cooperation. I do just simple tie switching. That might be the reason why I fail. Either or both could be, but I suspect actually bot might not change human behavior so much, even if the bot gets sophisticated in terms of sensing and acting. Because people also sense machine behavior and act to them based on their cognitions. So social norms are changeable product of interaction with people and technology. So people are likely to change their practice and strategy by machine intervention. So that means that I assumed human behavior doesn't change. Then if the bot estimates their behavior model, then we could do the better intervention. But actually, it's not like a clear statistics, but when I collect the data from humans with this personalized bot, they change their behavior strategy by the bot intervention. For example, actually some rational moves with personalization could negatively affect people in their decision making. The complicated bot behaviors could confuse people and destroy the social norms among them. So some participants actually left a comment saying, "We do not play like that neighbor." The neighbor indicated the bot. Okay, so they actually recognize we didn't identify the bot. We did not give the bot identity in this experiment. But especially for this personalized bot, they actually say, "Hey, I play with some neighbor who randomly play, or I play with someone probably algorithm, something like that." So people could treat the intelligent machine as random agent and give up cooperating with them in these settings. So here's a summary from the experimental findings. All in all, the study suggests the AI agent for public goods might need a different design concept from those for individual good. So for example, if we consider the individual good, I did not come up with the idea of the time management for this strategy. Since we humans are embedded in networks, assistant agent should leverage the network structure and dynamics that humans develop. The last failure, interestingly, suggests that machine behavior should have the maybe more sophisticated in machine learning, or have the simplicity and transparency of decision making, so that human could perceive the machine's thought and change their code of behavior. So in the personalization, I try to machine to recognize human behavior to act efficiently. But we humans do the same things. So that means that if the machine behavior is simple and clear to the human can adjust the bot intention to take an action. So that's why I think time management bot works so broadly. So that means that in the experiment, different people exist, right? Some people try to start defection, but time management bot work well for all the session. I think that's surprising. And last thing is that I think I think that these bots should be designed to help humans to help themselves by developing a new social norm or breaking an existing one. So on the one hand, I'm interested in that social norms. I recently interested in the social norm well. Social norms guide people to choose something easier. So for example, like in my experiment, so the bot actually creating a cooperative environment through the network intervention, then people can easily to cooperate in that setting. But on the other hand, social norms also work as constraint to trap people in suboptimal and preventing them from getting out of it. In that case, maybe the machine intelligence could break such an existing social norm to give a lead to the global optimal. So that means that sometimes social norm is good to guide people to go to the certain way, but maybe sometimes we need to break the social norm to get out of the suboptimal. So that is related to my previous work of writing noisy bot in the social coordination. So how could machine intelligence penetrate social norm among people? That's my ongoing research interest. And in the process of social influence, there are lots going on. So there are, of course, a network as a whole. There are one-on-one interactions between paired people. And there is what's happening within mind of individual people. And our intervention can affect all the layers. So I've studied mainly in the network interventions, but machine intelligence can work on interaction context and social cognition. So now my lab is expanding the research focus to include interaction and cognition layers. So closing my talk, I really touch on one of my ongoing projects. So including the iScience paper, I've been studying human cooperation and intervention to facilitate it. But in the real world, people are sometimes easy to cooperate, especially with someone in their own group. So for example, you can probably cooperate with easily within the CHM group naturally. So you don't need to the extra effort or the external intervention, for example, bot, to cooperate within the group. But if the social environment is totally different like this, the cooperation is quite challenging between them because they identify them counterpart as not us, but them. People face difficulty working together with outgroup member called in-group outgroup bias. This phenomenon also has been studied as partial altruism from an evolutionary perspective. So again, we need large-scale cooperation beyond in-group solidarity to address pressing global issues such as wealth inequality, the recent pandemic, and climate change. I think you can agree. But in-group out-group bias can interfere with the problem solving. And as a natural development from my past work on human cooperation, my lab now explores the machine intelligence intervention in facilitating intergroup cooperation, especially. So to mitigate in-group out-group bias, we focus on actually the conversations, because conversation play a significant role in both cooperation and identity formation. So, however, the current usage of machine intelligence, especially on social media, seems to work against intergroup cooperation. So people escalate conflict with outgroup members when they are exposed simply to opposing view with given in-group context. So social media does not only show the opposing view, but also gives the context, in-group context to you when you see the opposing view. I think that's a problem on social media. So how can technology mitigate in-group favoritism in humans? We focus on the recent development of language technology. So that means the natural language processing or NLP. And the technology allows the machine to detect and transfer language styles in communication across distinct social groups. So it might be blur group boundaries in communication with outgroup members and facilitate intergroup cooperation. So now we are start testing the idea using a new experiment setup. So it would be wonderful if I could share the experiment result with you in maybe next year or so in this group seminar. So my point is here, you might know a lot about study, maybe you know a lot about the polarization study here. So here is people polarized, then how we can address the polarization. And I found that many polarization studies focus on the consensus. So that means if you see some experiment settings, the goal is to have something like to have a same opinion between the different groups. But I think that's unrealistic and maybe problematic. So that means that forcing people to forcing a diverse opinion into one single opinion is also problematic in terms of the value of diversity. But we need a large-scale cooperation. I think that's a problem that we have. So my interest is now is that how we can have the intergroup cooperation with keeping diverse opinion with that. That it's okay to having a diverse opinion on people, but in something for different topic, we might need to cooperate even with someone who have a different opinion. Then machine intelligence might help us, or maybe suppress, to change this intergroup dynamics. That's my ongoing experiment. Okay, sorry for no data about the project, but I would like to happy to share the data if I collect it. So that's all from me. Thank you very much.